So let's start from the simple to the slightly more complicated. One of the things you can see yourself with a pair of binoculars is if you actually go out to a lake and there are boats on that lake, the farther away a boat is, the more the bottom of the boat will disappear, and you'll basically just see the mast of the boat. And as a boat goes farther and farther away, the last thing you will see is the very top of the mast of that boat. And that's because the boat is actually going over the horizon that's curved. And that means that as it goes farther and farther away, you see less and less of the bottom of it and more of the top of that. You can see that with binoculars. By an ocean, by a lake. It's really easy. That wouldn't happen if the Earth were flat. You would simply see the boat getting smaller and smaller and smaller as it went farther away, but you'd be able to see the whole thing with the same proportions. Now, another way that you can tell that we're on a sphere is to think about how there's something called the tropics on the Earth. And the tropics are places near the equator of the Earth where sometimes the sun is overhead in the sky. And this was actually something that the Greeks used not only to prove that the Earth was round about 2,000 years ago, but they actually measured the circumference of the Earth accurate to within just a couple percent. 2,000 years ago, we've known that the Earth was round. There was a really brilliant Greek scientist called Eratosthenes. And Eratosthenes noticed that there was a town called Syene, and on a certain date, the sun would actually shine straight down to the bottom of a well. That meant the sun was directly overhead. You could look down a well and see the sun shining back at you. And on the very same date, farther away in the city of Alexandria, that didn't happen. The sun was not directly overhead. It was a slight angle. And all that Eratosthenes did was he measured the difference in the angle of the sun. It was straight overhead in Syene. In Alexandria, it was a little bit less than overhead. And he rationed that that change in angle from one city to another was probably indicative of us being on a curved surface. And you could make all kinds of measurements, even between those two cities, and see that the angles were different. The sun was at a different place in the sky. Using this, he actually measured the circumference of the Earth, and he got it right 2,000 years ago. So another really simple proof is that on any given date, at different cities and different places around the world, the sun is at different angles in the sky.
Question 5. Is the Earth very, very small, or is the Sun very, very near? Eratosthenes' calculation of the Earth's circumference is dependent on the light from the Sun being parallel, as it should be if the Sun is 93 million miles away. But anyone can go out on a sunny day with broken cloud and see that the light that arrives on the Earth is not parallel. The light rays come down at angles, indicating that the Sun is actually very close. Now, the official explanation is that the Earth's atmosphere refracts the Sun's light, and that's why the light comes down at diverging angles. So, if the light from the Sun is always refracted, then that would mean that Eratosthenes' calculation was made with refracted light, and therefore must be wrong, and the Earth must be much, much smaller. So which is it? It seems to me that if you still claim that Eratosthenes' calculations are correct, then the light cannot be refracted. But if the light is not refracted, then the Sun is close. And if the Sun is close, then for Eratosthenes to observe what he did, the Earth must necessarily be flat. Question 6. In a similar vein, how does a convex lens make light diverge? So again, the official explanation for diverging sun rays is that the Earth's atmosphere refracts the Sun's light like a lens. But the Earth's atmosphere is apparently a convex curve, so that would act like a convex lens and converge the light, concentrate it like a magnifying glass. You'd need a concave lens to make light diverge as we observe. Now, some have said that it is actually the angles between layers of clouds that seem to make the light diverge. But again, observation says that this is not the case. Here, there is nothing between the plane and the cloud, and the light is clearly diverging. And this NASA photograph is taken from above the clouds. And still, the Sun's proximity is apparent. So, how does the atmosphere make light diverge?
Then there are some other proofs that are a little more obscure, but they're actually really lovely. And one is to observe what happens during a lunar eclipse. Now, a lunar eclipse happens when the Earth casts a shadow on the moon. The moon actually goes dark. In fact, if you've seen one, you can actually see the Earth's shadow go across the moon. And when the moon is entirely in the Earth's shadow, the moon looks kind of dark and even kind of red colored. It's really, really beautiful. What's happening in that case is that the sun is on one side of the Earth. The Earth is in the middle, and it's casting a shadow. The Earth is casting a shadow on the moon. And as the shadow moves across the moon, you'll notice that the shadow is curved, it's round. So something like the sun that's bigger than the Earth and is able to cast a shadow of the Earth on the moon can actually show you the shape of the Earth. Aha, you might say, but could the Earth be a disk? Could it be flat, but it's actually still shaped like a disk, not like a sphere? There was a Greek scientist called Aristarchus, and what he noticed was that you can get a lunar eclipse at many different angles where the sun is. Sometimes the shadow goes straight across the moon. Sometimes it just kind of glances the moon. Just a little bit is in shadow, just on the top or on the bottom. From every different vantage point, every different angle that the sun is casting a shadow, you always get a perfectly curved shadow. The only shape that can cast a shadow that's curved from any direction you put the light is a sphere.
Go over some animations. Our objective is to get the shadow to start in the lower east of the moon. For the duration of this video, you, the spectator, will be taking the vantage point of the sun and shedding some long-needed light on the subject. The Earth will be moving between you and the moon. Remember, our objective is for you, the sun, to cast light on the Earth that will start a shadow down in the lower eastern corner of the moon. Bear in mind that the official narrative is that the Earth is passing between you, the sun, and the moon in perfect alignment. From your vantage point, you're also going to have to keep the moon lighted as it passes behind the Earth. Just a real quick note on the graphic that I have displayed. The official narrative is that the sun appears the same size as the moon because it's 400 times further away. So in their graphics, what they do is they move it about 300 times closer, as opposed to the 93 million miles away. They do this because it's the only way they can trick the spectator into thinking that the sun is capable of producing a penumbra. To produce a penumbra, it requires a light source much larger than the object blocking it. If this were reality, this is what you would see. You wouldn't see this because this can't produce a penumbra. And without a penumbra, you can't have a 2,159 mile wide object cast a 70 mile wide shadow. With that said, let's get on with our animated demonstration. You won't find them giving you an animation of this, only still pictures, because they can't reproduce it animated.